So let's make sure this is recording. With sound too. Let's make sure this is recording. So let's make sure this is. Let's make sure this is recording. Let's make sure this is record. This is recording.
Is there sound?
Through what?
Why don't you just record it through OBS?
I am.
I thought you were live streaming to YouTube.
Yeah, I'm doing that too because I don't want to save the with sound too file on my computer. Why is there no sound?
So the main thing, you just want to make that.
Let's make sure this is recording.
All right, there's sound. All right,
So let's make sure this is.
That's good. So that's gonna loop for a minute, but cool. All right. So nice to see everyone. Let's go. Factoring with rational exponents. I changed the date. This was supposed to be due today, so I shifted it 24 more hours. Given that I had 3 emails, I sent some videos out, but yeah, let's go on with this. So to remind us to factor, we want to take out the smallest exponent. Well, in this case, actually, let's go with the number of parts. We have 10 and 5. The greatest common factor is 5. Moving on, we have a group of 8x minus 1 in between these two terms. So reminding us, a term is separated by addition or subtraction. You take out the smaller exponent, and you should know 3/5 is smaller than 8/5. We also have a common group of nothing. All right, so there is our common factor, 5 times the group 8x minus 1 raised to the 3/5. And ultimately, I was trying to rush this last time, but what we're really doing is kind of taking this 10 right here, which I will highlight with a highlighter, not an eraser, and dividing it by 5 to get 2. So I'll write that in just a second. We're going to take this group right here, 8x minus 1 raised to the 3/5, and divide it by the same base, which happens to be a group, but it's the same base to the 3/5. And so when we do that, 10 divided by 5 is going to become 2. And 8x minus 1 to the 3/5 minus the same base to this exponent, we subtract them. 3/5 minus 3/5 is 0. So that ultimately just becomes a 1. I'll put that there. And then we have this remaining factor of 2x plus 7. Now we do it again. All right, so we're going to take the 5 and divide it by our GCF 5. That becomes 1. And we're going to take the group 8x minus 1 to the 8/5 and divide it by 8x minus 1 to the 3/5. They're the same base. We subtract the exponents. 8/5 minus 3/5 is 5/5, known as 1. So in clarity, we'd have 1 times 8x minus 1 to the 1st. GCF out front, that's what remains inside. We can clean some stuff up. Leave your GCF out front. Let's focus on what's going on inside here. This is 2, which we're going to distribute into this binomial. This is 1, which we'll distribute into this binomial. And finally, we have 5 times 8x minus 1 to the 3/5 times 12x plus 13. And you now have a factored form of that expression. All right. I think I'll skip this last one, second to last one, and go to the last one because it has just a little more complexity to it. All right, so one last time. Let's look at the number of parts. We have 4 and 9. Their greatest common factor is 1, so that's pretty pointless. We definitely have a common group of 3x plus 2. This guy's raised to the 2/3. This is raised to the negative 1/3. So we're going to factor out the smaller exponent. Smaller, if I think of a number line, 0 is small, then the numbers go bigger. But if you keep going left, the further left on a number line, the smaller it is. Negative 1/3 is smaller than 2/3. Two x minus 1 is also shared between the two terms. 5/7 is smaller than 12/7. We have a 4. All right, talking this out, this group divided by this group is the same base. So 2/3 minus a negative 1/3 just becomes a positive 1. This group of 2x minus 1 divided by the same group, get the vibe, subtract the exponents. 12/7 minus 5/7 is 7/7, which is the same as 1. 9 still chilling there. One final time. This blue group divided by that definitely is just going to cancel out nicely, as will that one. They're exactly the same thing. So kind of not dragging this on any further, we'd have just this plus 9 remaining. Clean this up, bless you. 3x plus 2 to the negative 1/3. 2x minus 1 to the positive 5/7. Some algebra to do here. I'll distribute the 4. That's going to become 12x. And then 12x times, that's going to get messy. So let me just back up here. So I got 12x plus 8, which then needs to be FOILed into this guy. Okay, that's cool. Guess you can do that. So this is going to be 24x squared minus 12x plus 16x minus 8 after you do all that distribution, plus 9 for a final answer of, well, a couple things. This is just going to clean up in a minute, this big group at the end. Here's a negative exponent, which we're just going to write in the denominator. So I'm not doing this as quickly as I did at the end of last time we were together. Here's that, has a positive exponent, stays put. This is going down below, change the exponent to positive, and then we're going to get this quadratic factor of 24x squared plus 4x plus 1. and voila, like magic. It looks absolutely insane. I could see how no one can't be afraid of that at first, but hopefully with some color coding, I use the word groups intentionally, so we can kind of just say it's a group, it's a blue highlighted group, it's a blue highlighted group. They're the same group, they're the same base. And so when you factor something out, you're really kind of just subtracting the exponents there, right? It takes practice. It's worth the practice. Not all of calculus is that hard, but there are opportunities and examples that do come up that have meaning where you need to be able to work with fractional exponents and factoring the expressions to get somewhere useful. So this isn't just to make your life miserable. It is good practice for calculus, but not to scare you. Like, oh my God, I'm not going to calculus if it's like this. No, there's a lot of easy algebra things too, but I digress. All right. So that's where we left off at a rush at the end of last class. And I know I got a few emails, so hopefully that was resolved. If you still didn't complete that one homework, again, I've moved the deadline just on that for 24 hours, so you can finish up what you need to there based on the emails. Right. Okay. I'll try this again. It's probably the same thing. All right, there we go. All right, so moving forward, what I sent out through email form, if you didn't see it, was, hey, we have an exam next week. I wanted to move the date, given the snow date, but then I was like, oh, midterms are Wednesday, and I want that, more importantly, to be reflected. So I'm definitely keeping the exam 1 week from today. All right, so next Tuesday, exam 2. And things have even evolved since that email. All right, so given, like, at first I'm like, oh, I don't want this to carry into spring break, and this all just fits together nicely. So that's my side of it. That's not your worries. But in hindsight, looking at what we need to do and the importance of it, and given the fact that snow days happen, it is what it is, we're just going to let it go. All right, so tonight will be, I don't want to say aggressive, but there'll be very little downtime today, right? We're going to keep moving for the next 1 hour and 20 minutes, straight through. I'm ready to go. I have 7 lessons ready to go. We're not going to get through 7 lessons, but I'm not stopping once I get going. With that being said, there won't be any additional homework in terms of lecture videos. You will have enough to practice on whatever I get through. This won't really be a group work day, all right? So I'm telling you, I'm giving you a heads up. It's probably not the best way to teach, but we need to lock in for the next hour 20. There'll be opportunities to share out and turn to a neighbor, but we're going to keep moving and just do our best to get through this, but not sacrifice learning and understanding along the way, because that defeats everything I stand for. All right, so.
Will the video lectures be in what's going to be in regards today or from the last lesson?
So I'm saying I'm not even going to push the video lecture on you. So that thing that I mentioned, I said, oh, when you go home, if you saw the email, I said, there's going to be a video lecture after this. That's just too much, all right? So you're here in lecture tonight. Thank you for coming in. It's being recorded. You're just going to go home and do regular homework. But I will say this. I know, because I look at the times and study habits of everyone, just because I like to run those reports. And most of us do our homework Sunday night or 2 hours before class. Like when I checked all the homework that was due today, 1/3 of us had it complete. 2/3 of us haven't even logged in. So you're not alone. 2/3 of you didn't even log in till at least noon today to get your homework done. If you do that with the homework that's already posted, given that there's an exam in a week, you might as well just drop the class. And I can only say that as honestly as possible. You will not be successful. You need to have a plan as soon as you leave this class that says, I'm going to put time into my math homework. Have to for the exam 1 week from today. Here we go. Power functions is what we're going to start with. The end game here is this. That's from our syllabus from the school. I'm telling you this. You're going to add 5 more toolkit functions. On exam 1, I said you need to come in knowing square root, absolute value, and parabola. I'm telling you right now, you need to come in knowing 5 more. They're about to come up here. They're called power functions. We're also going to learn something called end behavior that uses limit notation. Some of us had some calculus background. Most of us haven't. It's not limits for those who have had calculus backgrounds, but it's the notation, the symbol of limits that's used in calculus. Those are 2 different conversations. And if you've had no calculus, this will be fresh to you. It's just new symbols. And then we'll look at a quick application that uses technology. From there, we'll move on to polynomial graphs. And I'll discuss the main goals then. But for right now, 5 graphs, limit notation, and be able to look at an application. All right, so a power function literally is a number times x raised to a number. For instance, 3x squared is a power function. For instance, 8x to the 1/2 is a power function. 9x to the -3 is a power function. Pi x to the pi is a power function. These are all a times x to a number. Now this one's silly, but we really can't do it justice until calculus. But you will know these 3 graphs in the next 15 minutes. End behavior using limit notation. Bottom line up front, it stands for what happens on the ends of our graph. That's really it. That's way more wordy than it needs to be, but it's there. End behavior, for instance, for a parabola, rises on both ends. It's that simple. The end behavior of a line, well, let me go back here too. A parabola that opens upwards rises on both ends. The end behavior of a line that increases falls on the left but rises on the right. That's end behavior in a nutshell. As x becomes very positively large, stands for really the right side of your graph. And the way we write the right side of the graph right there. As x becomes very negatively large, so like -10, -100, -1,000,000, negatives further outwards, stands for the left end of your graph. But the symbols that we use look like that. We will say the limit as x approaches infinity of this function, and then we got to answer it. That's coming up. the limit as x approaches negative infinity of whatever function we'll look at, and then we're going to answer it. This is kind of like an incomplete sentence. We have to actually finish it, but we're not quite there yet. This is the symbol that stands for what the heck is going on the right end of your graph. It might be rising. Turns out I could have opened this probably now, or it might be falling. And then this is the left end. Okay. Underneath it, it says the result is either going to be a number, positive infinity, or negative infinity. So we'll write this, and eventually we're going to say equals one of these three things: a number, infinity, or negative infinity. We do that for both ends of our graph. We're going to learn 5 power functions. We're going to write their end behavior, and there's more to even pop up here. So, for instance, let's get to it. Power functions: x squared, x to the 4th, x to the 6th, x to the 8th. These all fit a very nice family. They're all positive exponents. They're all even exponents. They don't contain any decimals or fractions. So we call those positive integers, even positive integers. And we know one of them, so it turns out we know a lot of them. They all have this structure. At the end of this lesson, I'll show you what I mean by that on Desmos. I don't want you to say, wait, they're all the same graph. No. For instance, if I input the number 2, this x squared graph would output 4. But if I input the number 2 here, it would output 16. So no, they're not the same graph. But they all have this feature that they're kind of U-shaped, that they curve around the origin. And that's what I mean by that. So anything that's x to an even positive integer power has this U-shaped curve, just like a parabola. X cubed, x to the 5th, x to the 7th, x to the 9th. I call it the chair. Because all I want to do is park my butt right there, lay my back there, and kick my feet down there. Looks like a chair. Again, not to say each one of these graphs is the same thing. Again, if you put in 2, this would output 8. Put in 2 here, it's going to output 32. So they're going to look not the same, but the same structure. They're all going to kind of arc upward and arc downward in that direction. Right. End behavior. Just trying to match the same colors. So I have right, red, blue, negative. This is how we write the left end. What is the left end doing? We can use the word rises, but in symbols, rising without any ceiling, just going up and up and up, is positive infinity. So the left end of that graph is rising. That's informal. Proper math notation, the limit as x approaches negative infinity is infinity. Okay, come back. The right end represents this, is also rising. So we're done. That'll be true for any x to an even positive integer graph. Right. left. I'll probably stop highlighting this after this example. But just to emphasize, this is the left. Notice it's exactly the same. It's basically how we say left. Now in this example, it's falling and there's no stopping. There's nothing stopping. It's literally arcing downward. That's an example of how we write falling without being stopped. We already seen how to write rising. So far, so good? Cool. All right, so know your limit notation and know that x to an even positive integer power looks like a U shape, to an odd positive integer looks like a chair shape. Negative integers. I kind of switched the order here on purpose, but that's okay. And last time we reviewed properties of exponents, specifically negative exponents are really reciprocals. A small output, like a half, that's pretty small. If you reciprocate that, it becomes 2. All right, so if you have 50 cents, you reciprocate it. Oh, you have $2. That's cool. Reciprocate something smaller. 1/100th. Reciprocate a penny. That's smaller than a half. 1/100th is smaller than a half. A penny is smaller than 50 cents. Reciprocate a smaller number, bro, you got $100. Reciprocate 1/1,000,000,000. That's so small. 0.0000. We don't even have a coin for that. Reciprocate that. It's huge. Got it? Small outputs reciprocate big. And vice versa. Take 1,000,000,000, reciprocate it. Now it's 1/1,000,000,000. Wicked small. Why do I say that? Trying to help you memorize less. You know x squared, don't you? It's a parabola. All of those are going to look like this. Just watch for a minute. Now, this right here on the parabola is a small output. It's not very high up. So on the reciprocal, it's going to be really friggin' large. Maybe this is a height of 0.5. So when we reciprocate it, it's going to be a height of 2. Or if this is representing a height of 100th, it's really large. This is how I memorize these graphs myself. This point on x squared is pretty large. So its reciprocal is going to be really small. And ultimately, actually, what's the reciprocal of, here's 0 on the parabola. What happens when we reciprocate 0? We had 0 on top of 1. So we have 1 on top of 0. We don't want to divide by 0. That's undefined. So actually, there's no output at 0. We're going to mark it like this to represent no output at 0. And at least in quadrant 1, we're going to get a graph that looks like this. Probably a little bit smoother, but that's good enough for me. I erased the parabola, but I'm going to talk about it. It's the same thing. Negative input, but the output's still a half. Reciprocate, it's going to be large. And this large part on the parabola reciprocates to something small. And I definitely don't want to cross that. There's the graph of basically, let me rephrase that, this is the general shape of all these graphs. Will this intersect the x-axis? Why not?
Because if you have a even power of a negative number, it becomes positive.
An even power of a negative number, it becomes positive.
We don't need the zero.
What's that?
We don't need the zero.
You don't need a zero. Not here. Is that what you're just referring to? Over here? I'm asking, will this ever output zero? Never. Okay, that is true. So why not? That's the consequence. But why won't we have it output zero? I'm looking, maybe you're saying I'm not hearing what I'm looking for. Thinking of x squared. So what's the output at like -10 or even +10? What's the output? 100. So what happens when we reciprocate 100? It's 1 over 100, which is still more than 0. But now let's go to -100 or +100. I don't care. The output is 100 squared, known as 10,000. And if you reciprocate 10,000, it's 1 over 10,000, like 0, but still that much above it. You're never going to output 0. And so you're saying things that are absolutely true, but I just wanted you to have the theory of it. We also have a horizontal asymptote. I heard the word. Okay, we're going to put that all together. Right here, this is the graph of all those functions, explained why. We have a vertical asymptote, as it's called, meaning it's not going to intersect there. It's going to get closer and closer, but never cross it at the y-axis. We also have a horizontal asymptote, which means the graph will get closer and closer this way at the x-axis. We'll write that in just a moment. What are the end behaviors? I think I'll stop color coding it. The left end and the right end. Let's talk about the right end. Is it decreasing? Is it falling? Yes. We're at a half, then 100, then 1,000th, then 1,000,000th. That's called falling. But you're not falling towards negative infinity. What are you trapped by? 0. And I just want to cursor back up here. The result of end behavior could be positive infinity. If you're rising and there's nothing stopping you from going higher and higher and higher, like a parabola opening upwards or a parabola opening downwards, there's nothing trapping that from going as negative as it wants to be. However, even though that graph is falling, this graph right here that we just at is falling, it's not falling free limit, no pun intended there, free will. It is trapped by the horizontal asymptote of 0. And that's what we write right there. That's the end behavior. And that's going to be true on that side as well. So if you're feeling brave, you have this chair graph that I told you should know. On the chair graph, this is a small or big output. So its reciprocal is going to be up. On the chair graph, is this a big or a small output? So it's reciprocal. So it's doing the same general idea as that. Small and negative reciprocates to, let's talk it out, -1/2 reciprocates to, does it change sign? No, it's still negative, but bigger, negatively bigger, -2. This is negatively big. Like, use an example, -100. Reciprocate does not change its sign. So it's still going to be below the x-axis, but it's just going to be a small below. And there's basic shape of all those graphs. And behavior again is approaching 0. This is rising. It is going, right? If you read it this way, you say, oh, it's rising on this end. It's kind of getting close, but it's not rising forever. It's trapped by 0. This is falling, but not falling forever. It's trapped by 0. So it came up. Let's officially talk about them. Let's just look at one specific example. Here's a nice, clean graph of, the way I think about it, chair graph. And then small outputs are big outputs are small, negative or small or big, negatively big or small. We call those 2 branches. More on limits. I want to actually jump down to this part. That's the stuff, I'll read this. So horizontal asymptotes. As we take the left side or the right side, the graph was getting closer to 0 on its ends. So horizontal asymptote because on its ends, it was getting close to 0. And when your ends get close to a number, that's truly the definition of a horizontal asymptote. And that's what I'm arguing right here. When your end behavior is not infinity or negative infinity, when it's a specific number, you have a horizontal asymptote. And the equation of that asymptote is y equals 0, flat line. Vertical asymptotes, on the other hand, there's been a change here. As x gets close and closer to 0 from the left. That's what that means. Before we digest it, this means as x goes smaller and smaller and smaller, just keeps going down, the end. This means as x moves further right. Now we're saying as x, not on its ends, approaches a number. So looking at this graph, that means as the x values get closer to 0, what's the graph doing in this area of numbers? What's the graph doing? What are the outputs doing? There go on the left side, what is it doing? Negative infinity. It's going downwards. And this means as x gets closer and closer to 0 on the right side. So graphically, that means What is the graph doing for these X values? Well, here it is. This is what the output's doing. It's rising, and it's not trapped. This is the definition formally of what a vertical asymptote. As you approach a number and your graph is going zoom up, or way down, or both way up or both way down, you're going to have a vertical asymptote. I don't want to spend much more time with this because it's notation. It is what it is. You just have to learn to read it. It's like learning Spanish or French or math. It's literally saying, as you look close to zero on the left, what is the outputs doing? They're falling. That's what that means. When you look at zero from the right, maybe you should actually look at it. So we're saying, look at these X values. What's the graph doing? Opening up, it's going upwards. That's it. Versus the limit as X goes to positive infinity and negative infinity means the ends, the left and right ends. That's called limit notation. If it's your first time seeing it, which I'm assuming for most of us it is, you'll be thankful when you take calculus that you're kind of seeing it right now for the first time, because this is lesson 1 in calc, plus some more. What's up?
I'm just wondering if you're running the limit as X approaches 0 from the positive side, you put a plus sign or not?
Yeah, I probably got erased there, but it's there.
Okay.
Yep. I just want to end with saying its vertical asymptote has an equation of X equals. Here's the other thing about this limit notation. It's not in your homework. So we will get better at it by using it. All right. Let's use it in just a moment. Before we do, how many graphs do we have so far? We have X to an even positive integer, the U-shaped things, to an odd positive integer, chair graphs. If you know those two, and you listen to my conversation about reciprocating, you now have -2s, -4s, and -3s, -5s, -7s. You have 4 of your graphs. We have 3 more to go. So I guess I said what? 5 graphs? I lied. 7-ish graphs. 3 more to go. Let's look at if we have fractional exponents. And I want to start with the one we know. We know one of these. We know x to the 1/2 because last time we reviewed properties of exponents, and maybe you never heard this, but a 1/2 exponent is really what? Square root. And I told you on exam 1 to know square root. Boom. Turns out if you have a square root or a 4th root or a 6th root or an even root, which means you have a denominator that's even, they're all going to look something like that. Not identical, but that's good enough. Cool. So that's not really a new graph. I guess I didn't lie to you. You already knew one of these. Limit as X approaches positive infinity means the right end of the graph. Is it rising? Yes. Is there anything trapping it? No. Boom. Does it make sense to talk about the left end of this? Can we even input negative numbers? No. So it doesn't even make sense to talk about. No, because we might say undefined would make more sense. As we input more negative numbers, this thing's just undefined. So there's a difference between 0 is a number. 0 literally has meaning. Undefined is like no meaning. Can't. It's like you know. It's not zero. It's undefined. So there is a small difference there. And in general, we just don't talk about it. But good question. All right, 1/3 and 2/3, or 3/5 and 4/5. What's the difference? They're both odd denominators, so they're cube roots or fifth roots or seventh roots. But look at the numerators. One side's odd, one side's even. I'm just going to tell you this. We could explore it. We could talk about it. There's only so much that's interesting, though. Turns out you're going to get this graph. Here's my quick answer as to why, if we had more time to explore it. This is a cube root. That was our build up to this, which is the inverse of y cubed. And I said it so briefly, but I said an inverse and its functions are reflections over the graph y equals x. You might have remembered that one graph where we reflected over y equals x. So if you had a cubic, its reflection looks like that. Same argument over here. That cubic chair graph has a reflection that looks like that. So there's my quick proof of it, not just telling you how you could come up with that. But at some point, these are just like must knows, all right? The difference here, let's take the time and build this one. If this is a cube root, let's put in a number, like 8, it outputs 2. And if you input -8, can we take the cube root of it? Yeah, it outputs -2. We good with that? Now let's talk about 8 again. Take its cube root, outputs 2, then what? So it's 4. So it's still going to act like that. But what about at -8? Its cube root is -2, but what happens when you square it? It goes back to positive. So because there's an even exponent on top, you get this graph that we say has a cusp, a sharp point, similar to like an absolute value, but we call that a cusp. Also majorly important for calculus to recognize there's a cusp there. And actually this guy, this could be a little funky once in a while. It's not a cusp, but there could be some interesting things going around near the origin. But I keep talking about calculus because I'm excited for you guys to take it. And it's really not scary. It's like, I'm just letting you know, these are must knows. I'm not wasting your time. These will things that are absolutely coming back. But anyways, I digress. Let's talk about these end behaviors. The limit as x approaches -infinity means the left end for this function is -infinity. It's falling. It's not bounded. It's not falling like a parabola, but it's not getting closer to anything. It's just going slower, but it'll eventually get as negative as you want it to be. And the same is true on the right side, except it's rising, maybe just not rising as fast as x squared. But there's literally nothing stopping it. Quick answer, quick example. Cube root again. Input 8, outputs 2. Cube root of 100,000 is eventually 100 or something like that. But it is going up and up and up. All right, 100 cubed, outputs 100. So it will go up. End behavior here. Both the left and the right are rising. I said 5 graphs. Did I lie? Did you already know x squared? Yep. So nothing new there, except extend it to x to the 4th, 6th, and 8th, and whatever. Maybe you didn't know x cubed. So there's 1. Reciprocal of U-shapes, reciprocal of chairs. Small become big, big become small. Okay, those are new, but not hard to remember. So 2 new, 3, You knew square root, so I'm not counting that one. But just reminding you, it's anything with an even denominator because that's an even root. That's connection to last lesson. And then 2 right here. So really 5 new graphs. Here's a quick opportunity for me to bark less at you. Let's use this graph where n is a non-zero integer. What is the exponent? Well, we can't say exactly what it is, but we can say what it's not. Is it 2, 4, 6, 8, 10? Does it look like a U-shaped connected parabola? Definitely not. Does that look like a chair graph? No, that is not a chair graph. A chair graph is connected. Definitely has 2 asymptotes. That's suspicious right off the bat. What graphs do we know have some asymptotes thus far that are power functions? Negatives. Now we know 2 graphs. These are like negative, oops, my bad, I'm writing the wrong thing. This is x like the -2 or anything even, or we have like x to the -3 or x to the -1. Which one is it vibing more like?
Negative, even.
Negative, even. Do you agree? Yeah, because it's like 2 branches that are both going in the same direction. But what transformation might have flipped that?
A equals a negative number.
Dude, what the heck just happened there? How come? If it was like x to a -2 or -4, it would be opening upwards like that, right? What do we know about transformations? What do A values do? They can reflect it over X. Like a parabola, right? Do you guys follow what I'm saying? Like going back to transformations. So let's put it all together. -2, -4, -6. That's an even n. But it's negatively even. We in agreement? What's true about the coefficient? What's true about A?
Negative.
Has to be negative. What interval is this graph? Are the y coordinates, are the outputs positive? Where do we have positive y values? None. I'm seeing hedge, none. Good. You're learning how to read math symbols and how to compare to a graph. What intervals is it? When I say it, the function, the y values, the outputs, whatever word you want to use there, when is it negative? Negative infinity to 0, 0 to infinity. But there's no output at 0. So don't say at 0, because that would assume there's a y value that's negative. There is no output there. Is this an odd or an even function? To remind you what that means, if it's symmetrical about the y-axis, like a butterfly, like a parabola, it's even. It's even. Like, while we're at it, what does it mean to be an odd function? It's called reflective about the origin, a phrase I hate, but it means, really quickly, detour, it means if you had a graph like this, you rotate it 180 degrees. So you say, hey, rotate down here, and it's going to look like that. So I wish we called it, are you kidding me? Like, I'm really not going to deal with this all night. It might be the connection. It's like a 180 degree rotation there, okay? Identify the equations of the asymptotes. The equations of the asymptotes is not the same as the behavior. It's not the limit definition. It literally just says, what are the equations of the asymptotes? Our vertical asymptote right here. What's the equation of a vertical line? X equals 0. That's your vertical asymptote. And right over here is your horizontal asymptote, y equals 0. What's the limit as x approaches negative infinity? What is the left end of this graph doing? What is the right end doing? What is the limit as x approaches 0 from the left? What is the limit as the x values approach 0 from the right? Negative infinity. Already better in 10 minutes. And when you get to calc, you're going to, if this is your first time, you're going to be like, wow. Your classmate's going to be like, I'm struggling a little bit. You're going to be like, nope, I'm good. I already got that out of the way. You're already ahead of the game. So we said 0, 0, negative infinity, negative infinity. And that's a pretty standard test question of mine. Sometimes I ask everything there. Sometimes I do pieces of that. All right. So I'll let it go. Power functions are done. Meaning, did we talk about some powers? Yes. What powers? Evens, even integers, odd integers, both positive and negative, and fractions. We did not talk about pi to the pi because we can't. It's just too weird and it requires calculus. So I'll leave it there. But those are the graphs you should know. Model real world phenomena. I guess we didn't really do that. I deleted that off now that I'm relooking at it, and it's not really that important. All right, I'll let it go. So that's what I want you to know. So I'm going to cut that off as an objective. We didn't do that.
What is
Yeah, I don't know. I'm going to try changing the connection really quick.
You want me to disconnect one?
You're not connected to the LAN. No.
It just kind of baffled me that the number, as they get closer and closer, they never reach the 0.
Because essentially what you're describing is a number that becomes infinitely close to 0.
Mm-hmm.
Yeah, but because of the 0, it will never.
It'll never reach. Because as long as you have the input's being reduced by like a multiple or by a fraction, so you'll never reach 0 unless you start with 0. And since 0 is an asymptote, you'll never hit it.
Oh, because 0 is an asymptote, so it can't hit it. No matter how big the number is, it's just going to go as close as close. Is it at one point?
No, that's all. I promise you, all in the homework. That's all you need. I went through it seriously as a student. Make sure you could, if you got to know those shapes. So that's like when you study for this, there's a difference between like doing your homework and then saying how well you know it for a test. So if you're looking back and saying, wait, what's that shape again? You don't yet know it. So I'll say it one last time in case you missed it. The way I do, this is just me. This is how I summarize it. I already know x squared. So it's like x to the 4th, x to the 6th. It's a U-shaped graph. Yep. Then I call the next ones the chair. That's just me. If you don't like it, you come up with whatever you need to. But I call it a chair. Got it. Then I bang out the next two by thinking reciprocals. So if I have a small, its reciprocal is large, and a large reciprocates to small. So I think of a U shape, and I literally showed you what I did in the video. Flip it. And I can get both negative x squareds, x fourths, x sixths, and negative x ones, x cubes, x threes. Lastly, fractional exponents. Let's start with what we already know. Square roots is 1/2. That's called an even root. So blank over 2, anything over 4, anything over 6 is going to just have that square root vibe. Then there's basically 1/3 and 2/3 odds. 1/3 square root vibe, but also allow negatives. Kind of like cheat sheet here. And then even on top of an odd, square root vibes, and that thing that was down here is now in quadrant 1, you get a cusp. That's how I know it. And that's how I studied it since Calc 1 myself. We're moving forward. We're going to talk about polynomials now, something that always is talked about. But what we need to be able to do for our course and to be successful in calculus is basically understand what the zeros of polynomial functions are. And in that comes up graphs and tables and stuff like that. Briefly, probably for the last time, I feel like every time I took a math class, whether it was like college algebra or pre-cal, always redefining polynomials. So, we're in a pre-cal, let's just bring it back to life. What is a polynomial? Basically, they're power functions where the exponents are 0, 1, 2, 3, 4, 5, 6, 7, 8. No negative exponents, no fractional exponents, no funky exponents. But it's basically just adding or subtracting power functions. That's kind of a cool way of thinking about it. So for instance, just kind of want to talk about, that's a power function. That's a power function. We can add a different power function or another power function. And there's a polynomial. It has many power functions. Now, this is a power function, but a polynomial does not allow negative exponents. This is a power function. A polynomial does not allow fractional exponents. A polynomial is basically power functions with only positive integer exponents. Don't overcomplicate it. You don't need to know its definition by heart. You just need to say, yeah, that's a polynomial, and no, that's not a polynomial. Why? Like, literally, why?
They do not have negative exponent.
No negative exponents.
And fractional exponent. Okay. Thank you.
Now it's not even connecting. Really?
Maybe they think angle with you. Just an angle with you.
Yeah, it really is. It's because it knows I have a busy night and it just doesn't want to be nice. Yeah. Yeah, amazing. All right, so other things I want to just briefly remind us. Degree is the highest power. And almost always, except once in a while, for some reason, the author of a question doesn't put it in what we call standard form. But when it's listed from highest power down to its lowest, that's called standard form. Polynomial graphs, just things to briefly know. There's no sharp points. They're always smooth or kind of just linear at points. But there's no sharp points. There's no cusps. That's a new word I introduced tonight. And there's no breaks. There's no holds. There's no asymptotes. There's nothing. I call them like roller coaster graphs almost. It's like that'd be a fun roller coaster to ride.
Let me ask a quick question.
Go ahead.
If you have absolute value function, is not polynomial function?
Definitely not. It's got a sharp V. Yep. No.
Thank you.
Yep. Dominance and leading coefficient. So it's literally saying the same thing. Sometimes it's called dominance. Our textbook called it leading coefficient. I didn't realize until I started teaching calculus how powerful it is to know who dominates someone else, like what functions dominate. And so I want to end this course later sending you with that, but we're not quite there yet. But we can start to introduce this. Basically, the highest power is the most dominant. It's going to win in the long run. I'll show you what that means when I open up Desmos, because I said I want to show you the graphs nicely at the end. But for right now, just take a leap of faith and trust me. The highest power wins in the long run. So therefore, if we need to determine the end behavior, we only need to look at the highest power. That will determine the end behavior of the polynomial. So a typical easy question, if you know it, you know it. If you don't, you don't. The graph of negative 5x to the fourth minus x cubed plus 7 falls to the left and rises to the right. How we answer something like this is using the leading coefficient / dominance. Think about the power function negative 5x to the fourth. That's a U shape that opens down. So my claim is this is the dominating force in here. This determines everybody, like this overall end behavior. So now, does this fall on the left? So far true. And rise to the right? No. False. Who's the dominating force here?
Negative x.
Negative x.
Ne-
Negative x to the third.
to the third.
Yep. So it's not in standard form. Just pay attention to that. Which we know is a chair graph that's been reflected. So something like that. Now this is not limit notation, but this is in our homework. They don't quite take you to the limit, but I took you there. But this is pretty close, right? So can you make sense? What side are we on?
As x approaches infinity, so on the right.
On the right. Is it going down? Is the right going down? True. So far, that's a true statement. So that's all I can say. I wish they told us more, but it just says, is this statement true? Yeah, that statement's true. It's an incomplete statement about end behavior. So last night in my pre-calc class, students like, well, it's incomplete. And I was like, yeah, that's fair. But based on this one sentence so far, it's telling the truth. So we have to assume it's true. All right. Zeros. X values that make the polynomial equal to 0. I think I've mentioned that already a few times in the course. Doesn't hurt to hear it again. Graphically, they're x-intercepts. Fancy word for x-intercepts, fancy word for saying, hey, what makes 0? So way too simple. What are the zeros of this function? 3 and 2. Because if you input 3, it would output 0. If you input 2, it would output 0. Now, if you graph that 1, 2, 3, 1, 2, those are called x-intercepts. That's all. Zeros are the same as x-intercepts. Multiplicity, long story short, refers to how many times a 0 is repeated. Really, really quick example. We're going to look at putting exponents on these groups. Now, we're going to say 3 is still a 0, because if you input 3, it outputs 0. But we're just going to say multiplicity of 2. It just means, that's what it means. It's just twice. If this was 5, we would still say 2 is a 0, but it's multiplicity of 5. You got it. I'm just abbreviating quickly. I have it more formally laid out in just a second. Furthermore, if you have an even multiplicity at that x-intercept, the graph is going to turn. It's going to look like a U shape. If it's odd, it's going to cross through. That's what this says. So we're going to crunch through a bunch of these. What's one of the zeros?
Positive 2,
What's the other one of the zeros?
6,
What's its multiplicity for each one?
1.
Yep. So at the x-intercept, it's going to cross. We'll come back to that, promise. Again, take a leap of faith. Just for a few more minutes. Next. What are the zeros?
Negative
Mm,
4.
why do you say 0?
Oh, wait a minute. No.
Let's try putting it. The quick answer is let's just check. If I put in 0, this is going to become 16. This is going to become negative 5. 2 times 16 squared times negative 5. Not going to make 0. Negative 4 and 5. What's its multiplicity? 2 and 1. Which means at this x-intercept of negative 4, it's going to turn. At this one, literally 1, it crosses.
So it has nothing to do with, I'm sorry, it has nothing to do with the factor of the 2 there.
Nope, has not. This is just a transformation. This is just vertically stretching that graph.
Okay,
That's all.
thank you.
I know you guys are going to tell me 2 and negative 2.
Yep.
You're going to tell me their multiplicity is
2.
2 and 2. And so,
And yes, they're going to
and they're both going to turn. It's that simple. It's almost like I don't want to do this anymore.
It's just about if they're even or off.
Yeah, that's it.
Okay.
Backing, yep.
All right. Sure.
Multiplicity, even, turns around. Odd, crosses. What's one of the zeros? Hashid. 0, yes. All right, so 0 definitely makes this guy 0. Cool. What makes that 0? Can you do it in your head?
Yeah.
Add 9, divide by 2. The end. 9 over 2. You want to call it 4.5, you're going to get credit, but why even? That's an extra step. 9 on top of 2. Multiplicity, 3. Multiplicity, 1. So at the x-intercept, crosses through. What are your zeros? Oh, wait a minute. We have to factor this. So we're going to briefly review factoring. Number 1, is there a GCF? You should always ask, is there a GCF? Next, factoring trinomials.
Wait a minute. 36.
How many people knew that I haven't been telling the whole story about factoring trinomials, specifically if A is 1? Not many of us? Good.
What was your question?
If A is 1, so I want to focus on this.
Yes.
I never lied to you. I told you something's 100% true. So I just want to focus on that, and I probably shouldn't use red on red, so I'll use yellow on red. So pretend I just say factor this. What has been our strategy so far? A times C.
Yep.
Find the factor pairs that add to the middle, split the middle, group, blah, blah, blah. That's going to work.
Yep.
Here's a shortcut, but it only works if A is 1. This is why I held off. Because in my years past, quick side story. Why didn't you tell us a shortcut from the beginning? Because I wanted you to have that algorithm. Because it, one, always works. Two, students, there are times A is not 1. So everyone tried doing the shortcut all the time and the grades were terrible. So I took that out of my teaching toolkit and said, I'll eventually let them in on it, but not right away. So back to this. Only if A is 1, which it is, what multiplies to 36 but adds to the middle? -6 and -6.
Yep.
Then those are your two groups. Meaning, it's going to be x minus 6 times x minus 6. Here's my proof. Foil it out really quick. You get x squared. You get -6x and another one, and you get positive 36. It won't work if A is not 1. Don't do it. There's no shortcut. It's split the middle all day and night. But if A is 1, let's add that to our toolkit. And then since we're talking about multiplicities, let's write this in a nice condensed form as x times the group x minus 6 squared. So our zeros are 0 and 6. The multiplicities are 1 and 2. And at the x-intercepts, they will cross and turn. Let's sketch this thing's graph. How many factors of x are there right here? 1. How many factors of this group are there? 2. That's literally the multiplicity. You got it now?
Yeah, I was just gonna mix it up with something else.
What is the left end doing? Rising or falling? This is dominant. So it's a chair graph that the left end is doing what? Falling. Yeah.
You're not taking the top off, the upper part.
There's no trick question here. I asked, what is this polynomial's left end doing? You look at the dominant force, the left end is falling. So we're going to begin this graph with the left end pointing downwards. Which one of these numbers is going to come up first? 0. And what are we going to do there? Cross. Then we're going to come back around to 6, and we're going to turn. So it looks something like this in a smooth, continuous curve. You cross there. By the way, every teacher will tell you they're a pain in the butt to draw. You almost have to have a plan in place first. So I got to cross here. I'm going to start this way. And I'm going to come up to 6. Turn back around. And that's a quick sketch of it. That's all I want you to do. Recognize it can be tedious to draw and annoying to draw, but there is a quick sketch of this polynomial graph. The proof is when I show you Desmos. I'm just not flipping this thing. It's already thing. So you can say, I don't believe you. Continue to not believe me. I like that. But I'm not lying to you. All right. Is that factored? No. That's not a trinomial. How many terms is it? It's a four-nomial. It's 4 terms. But when we factor trinomials, the long method, I call it split the middle. How many terms did we get when we split a trinomial's middle? 4. What did we do at the point that we had 4 terms? What was the next thing after you split the middle? You did what? To the first, come on. What did we do after we split the middle? The GCF out of the first 2.
Yep.
Let's try it. There's 4 terms.
Yep.
Let's try it. What's the GCF of this?
X squared.
What's the GCF of this?
9, -9.
Oh my gosh. It's like it was rigged. Of course it's rigged. Of course it's rigged. And your homework questions are rigged too.
But how about you have x squared and the 9 there, can we combine it and factor it too?
Well, we take out the common group of x plus 5. And then you have x squared minus 9. Besides, Bo, who knows how to factor this? And I want everyone to say, I do. It's not a trinomial, but it is a quadratic. It's a very specific quadratic. It's called a difference of squares. If you forgot it, here it is. You get two groups. One with x, one with x, one with 3, one with 3, one's a plus, one's a minus. Don't believe me? Is this 1? Yeah, so we can use the shortcut. What multiplies to -9 and adds to the middle 0? Give me two numbers that multiply to -9. 3 and -3. That add to 0? There they are. Remember I said there was a shortcut if a is 1? There it is. So if you don't like a new formula to memorize, if you feel like difference of squares is something else new, then just apply the shortcut. But you should know a difference of squares. It's way too common, and it will be more common as we proceed in this course. We're done. Our zeros are -5, 3, and -3. They all have multiplicity of 1, which means their x-intercepts will all cross through. If I asked us to sketch a graph, it's going to be very similar to this, except we have -5, then at -3, and then a +3. It's going to start here, cross, turn, turn, and it'll do something like that. To get exactly this height requires calculus. To get exactly that depth requires calculus. Everyone thinks they're in the middle. They're not, okay? I don't care in this course if you sketch them in the middle, but I do care if you say, oh, to find that highest point, I'm just going to take the average. No, and no, all right? The middle is what's challenging. The goal of pre-calculus across the world is you can say, I know the ends, I know some stuff in the middle, and I'm ready for the next course. But it's not possible to say any more than that. And if you can say those things, given factored form or just some very rigged factoring, it's like I have to make sure these things factor. I just can't throw any numbers at this stuff. But if you know how to factor GCFs, 4 terms, and difference of squares, you're right where you need to be. I don't want to bury you too much, so we're going to end with this last example. What's the end behavior?
So -x⁴, that's the dominant, right? And that's what determines that behavior.
Correct.
And we know it's even and negative, so since it's negative, it's going to go facing downwards, and it's even, so downwards parabola, right?
U-shape.
U-shape, yeah.
Little side story, I'm not picking on you. A parabola is strictly x squared. X to the 4th and x to the shapes, they're used, but only the x squared is perfectly called a parabola. I'll show you that in like 10 more seconds, well, 2 to 3 minutes. But you're cool. It's a U shape opening down. Study with him. That's how you need to study. That's how you need to study. You need to say, it's the dominant, it's x to the 4th, so it's down, and there's a negative, so it's reflected. I can't even say it as good as you. You should be teaching this class. Hopefully the microphone picked that up. How do you write it in limit notation? You almost can't get it wrong when they do the same thing, which is nice. But we just say the left end is going down. and the right end is going down. Cool. What's the y-intercept? How come?
Because there's no transformations to make it to move it left, right, up, or down. So the center of a U is at the center. Origin.
No. This isn't a power function though. This is a polynomial function. So it could be really, if it was just a power function, then you had a stronger argument that there was no transformations. So the U shape is at 0. How do you find the y-intercept of any function in any math class? You sub in
The 0. The x.
sub in 0. What's the output?
0.
Thank you. So you got lucky, just not your justification.
I wish this one different.
Sub in 0, always and forever. Us math teachers like seriously joke about that. It's like, how many classes do you teach? And you tell them, if I'm teaching Calc 4, which I haven't, but I'm hypothetically speaking, I'll say, how do you find the y-intercept here? And students are so locked into like whatever calculus they just learned. It's like, oh, you didn't go over that. No, you're right, because it never changes. You sub in 0 no matter what math class you're in. All right, I'll let it go. 0, 0. Let's find the x-intercepts and describe the behavior there. By the way, former test question of mine. Just so you can kind of see things that you have to be able to do. Is that factored? No. Is there a common factor? Yes. And I suggest, you don't have to, but it's just going to be easier if you take the leading sign always. Because watch what happens when you do. If you didn't, you'd have something that's an eyesore, and you'd have to work that more carefully. But if you take the leading sign, you're good. Next. That's a difference of squares. So what are our x-intercepts? 0, 4, negative. I don't know what that is. I have no idea where my brain just went, but it was obviously not where it was supposed to be. There it is. Here's our x-intercepts. And what's the behavior here? Turn or cross? Turn. How come? Multiplicity of 2. What about here? How come? What about here? Cross, because multiplicity is 1.
Did you mean the x minus 4x plus 4?
Yeah, for the
Okay, that's right.
What are you talking about? Is this?
Eliminate the evidence and eliminate the
Well, I had an yeah. I tried to do that last video because I had an error. I think almost the same error. And I was like, how do I fix it? Like, I can't get the pop-up like they used to. I don't care if someone wants to show me another day, but not today. It's all good. But I don't deny making too many mistakes. But anyways, is this even or odd? I don't see the symmetry. Maybe it is even, but be careful. Just because the exponent is even doesn't guarantee. So that's why I purposely asked that question. You're likely to be correct, but here's further evidence. Let's plug in a number like 1. What does 1 become? And then -1 here, and then 16. So when we sub in 1, it outputs 15. How can I test if it's going to be even? What should I sub in? The other side of the axis, and it better output the same number. When I input -1, it's vibing, it's turning positive, so you're going to get a -1 plus 16. So there's like just stronger evidence. Don't fall in love with the even exponent. That's just a warning. It's not guaranteed. It's pretty likely, but it's not a guarantee. I would do a little more investigation like I just did. Even. Therefore, it's symmetric over the y-axis. Let's end with sketching this thing's graph.
So if we have an equation and we know where the x-intercepts are because we
Did the factoring. Yep.
Wouldn't I want to test whether my equation is even or odd by choosing values that are to the left and right of those intercepts?
So even or odd would have to be symmetric. An even function is symmetric about the y-axis, not anything to do with the intercepts necessarily. Oh, I see what you're saying, though. That would work, too. I see how you're thinking about it. That's a good, as I said, do a little more investigation, whatever road that might be. All right. The main point I wanted to share with everyone, which I've now brought up the third time, is like, don't fall in love with the even exponent. It's likely, but it's not a guarantee. And we could probably come up with an example pretty quickly to make it fail using that type of logic, but it's a little bit higher level thinking. Not that any you guys, you're okay where you're at. Let's sketch a graph of this, call it a day, and I just want to show you the Desmos graphs super cleanly. So putting it all together, we know it has to fall on both ends. It has 3 x-intercepts. The first one, that like the furthest left, is -4, and it's going to cross through. Then at 0, it's going to bounce. And then at 4, it's going to cross again. And it should hit 0, 0 since I have the y-intercept. And if you totally understand that and you put that together, you're right where you should be in pre-cal. So a quick sketch, that's all we need, nothing perfect. Down here, come up to 0 and bounce. Again, doesn't matter how high or low you go. And then you're going to cross at 4 again. It's falling on both ends. The y-intercept, the x-intercepts, cross, cross, turn. And with no time remaining, actually, clock says 5:38, so I still have my 2 minutes. Hey, the computer says I have different options for you. You can literally stop packing up, but we're going to let the computer win here, but only to some degree. So I can fly through this pretty quickly. X to the n. How I started tonight's class. If you have 2, it looks like that. Now, if I have x to the 4th, it's not the same graph, but it's the same structure. And x to the 6th is the same structure. It's that U shape. But also going back to what Gennaro said, only the red graph is a problem by, like, very specifically, all right? So just picking on the conversation, but that's it. That's all I'm going to say about that. Let's look at odds. Chair, chair, chair. 31's odd. That's a weird looking chair. But it's a chair. And if there's a negative in front of any of these, it's just a transformation. Boom. That's all. Okay. Let's talk about negative n. -2, -4, -6, -8. They're not the same. Last time I'll say that. But they vibe the same structure. -3, -5. Believe me? There you go. Fractional exponents, like square roots, 1/2. But that could be 4 or 6 or even 5, 6. It's not, yeah, there's some change there, but it's still having that overall kind of like arcing effect there. I'll let it go. If it was an odd, and we're zoomed too far out. And if it's odd, odd, but even on top of odd, there's your cusp graph. Okay? I didn't lie to you. Next, x minus 2, x minus 3. One of the easiest way to write a parabola. Its x-intercepts, 2 and 3. It passes through 2 and 3. But if I change this guy's multiplicity to an even, now it turns there. And if you change this one to even, now they both turn. Or if you made it odd, it gets a little funky. So let me just kind of give it a little more space. I'll change that to over there. And you're like, whoa, what happened here? I'll come back to that. Last night I did almost the same thing. And some students like, well, there's 2 different graphs. And that's actually interesting. Around -2, it looks like a parabola. And around 3, it looks like a chair. That's 100% true. But I said at the beginning, polynomials are continuous and smooth, and they're really hard to figure out how far down and high they go up. There's more to the story for calculus, but I don't want you to think there's 2 different graphs. But that was interesting. And that was interesting again. So literally, it's not just that they pass through or turn, it's that they look like their power function. But that was, I didn't even mean for that. But you guys got a little more Jeopardy knowledge there. Do your best on your homework. Do not wait till Sunday night. You need to have a plan. Don't let your life dictate your homework for the next 7 days. You have to say, here's my plan, and that's what I'm sticking to. You might have to tell your friends, not going out. I know you got jobs and kids and lives and girlfriends and boyfriends and all those things, but you have to lock in till spring break, all right? So I'll see you guys on 2 days from now, whatever that is.
Thank you.
Spring break's coming up.
Prof, can I say something to you?
Yeah.
If I'm writing sometime and I'm not paying attention, I get lost. Okay. Do you sometimes share your notes?
Yeah, I can share them.
Yeah, because
It's Alex, right?
yeah.
Yeah, okay.
What do I,
I will do that. I'll do that before I leave. You will, I don't know if there's anything you have to do. I think it automatically happens, but just check in the next 24 hours. But every time I've always done this, I know how to do it, and then students are in. So I don't know if you get an email or not, but cool.
because if